This is the third lecture for Text Unit 9 on gases and gas laws. Subject of this lecture is Dalton's law of partial pressures. I've talked about this before when we discussed Boyle's law, but let's consider the origin of pressure. Suppose we have a gas, in this case krypton, trapped in a box. The atoms of a gas are relatively far apart compared to solids and liquids and move around quickly. So here, for example, is a krypton atom moving around inside the box. Pressure is the result of collisions with the walls. Occasionally these moving atoms hit the box, and when this atom, for example, hits the wall on the left, it experiences a push to the right. The pressure of the krypton, according to the ideal gas law, should be equal to moles of krypton times R times T divided by the volume of the box. If I add another gas, say argon, represented by this pointer, here we have an argon atom bouncing around, bounced out of the box. There will also be pressure from the argon atoms, and that will follow the ideal gas law. The argon pressure is moles of argon times R times T over V. So you have a pressure from the argon and a pressure from the krypton. Notice that the temperatures of the two gases will be the same, at least if we wait a while. And of course they're trapped in the same box, so they have the same volume. And this situation will be true as long as the krypton and the argon atoms don't interact with themselves or with each other, which is a description consistent with the ideal gas law. Alright, here is a statement of Dalton's law. The total pressure is the argon pressure times the krypton pressure in our example. In general, if gases A, B, C are mixed, then the total pressure is the partial pressure of A and the partial pressure of B and the partial pressure of C. We call these pressures exerted by one gas partial pressures. So the total pressure is the sum of the partial pressures. And the partial pressure of any gas, partial pressure of A, will be equal to x sub A times the total pressure, where this, called the mole fraction of A, is moles of A over the total moles of gas. Okay, again, to re-emphasize this relationship, if we take the total pressure and multiply it by the mole fraction of A, defined right here, we get the partial pressure of A. Air is a mixture of oxygen and nitrogen and argon and water. The amount of water varies, and carbon dioxides. Here are the partial pressures of each of these gases in kilopascals. Oxygen's 20.9, nitrogen 78.1, etc. Sums to 101.3 kilopascals on a typical day. This is roughly 1 atmosphere, or the total pressure of air on a typical everyday basis. You could ask, what fraction of the air is carbon dioxide? From this figure, if we take the carbon dioxide pressure and divide by the total pressure, note that pressure units of kilopascals cancel, and we get a value of 0.0005, which is unitless. We can convert this to a percentage, 0.05%, by multiplying by 100. Okay, what we have done here is taken the partial pressure and divide by the total pressure to get the mole fraction. Okay, so again, Dalton's law was rearranged here to solve for the mole fraction of carbon dioxide. You can repeat this calculation with any other of these gases in this list and find the percentage of oxygen and nitrogen, etc. Here's another. Sorry about that. Here's another sort of typical problem. Mixtures of helium and oxygen are used in the air tanks of underwater divers for deep dives. For a particular dive, 12 liters of oxygen at 25 C and 1 atmosphere and 46 liters of helium at 25 liter and 1 C were both pumped into a 5-liter tank. Calculate the partial pressure of each gas in the 5-liter tank, the total pressure in the tank, and the fraction of each gas, mole fraction of each gas in the tank. Okay. First, we need to solve for moles of oxygen and helium. PV equals nRT, N is PV over RT. And we can solve for moles of oxygen using the ideal gas law. Notice moles are the units that survive, and they're in the denominator and the denominator of a fraction, so they come up into the numerator. There are 0.49 moles of oxygen, and I can make a very similar calculation. I don't even show the units here since they're identical to the situation above, and there are 1.9 moles of helium. Okay. Note, just as the problem doesn't ask for this, but just as a passing observation, the mole fraction of oxygen is 0.49 moles, plus 1.9 plus 0.49. Well, this is 0.204. Mole fraction of oxygen in this case is 0.204. We could find the mole fraction of helium always by subtracting 1 from the mole fraction of oxygen. Mole fractions always add up to 1, just like percentages always add up to 100. Well, the mole fraction of helium is 0.796. I just note that in passing. Once we have moles of each gas that go into the 5-liter container, we can calculate partial and total pressures in the container using the ideal gas law. P is nRT over V. We can find a partial pressure for oxygen and for helium. Oxygen 0.49 times the gas constant times 298. Divide by 5 liters, we get 2.4 atmospheres. Again, I show the calculation is the same for helium. I don't show the units. We get 9.3 atmospheres. Total pressure, P, is 2.4 plus 9.3, or 11.7 atmospheres. Mole fraction is 2.4 divided by 11.7, or 0.205. And 1 minus 0.205 is 0.795. Okay, notice what's happened here. Well, the differences in the mole fraction values on the previous slide are due to round off and etc. And it's out here on the last digit. Point is, once we find moles, we can calculate partial pressures and total pressures. We can use those to find mole fractions. And we get the same answer from Dalton's law that we get from just calculating the mole fractions as moles of each gas divided by the total moles of gas. Here's one more example. A 2-liter flask is filled with argon at 752 millimeters of mercury and 335 Celsius. 0.728 grams of benzene is added. And the temperature and volume of the benzene will be the same. What's the total pressure in the flask and the mole fraction of each gas? Pressure of the argon, well, I convert that to atmospheres. 0.989 atmospheres. Pressure of the C6H6 called benzene is 9.33 times 10 to the negative 2. It's found by taking 9.33 times 10 to the negative third moles, multiplying by the gas constant, multiplying by the temperature, and dividing by the volume. The moles here are calculated from 0.728 grams of benzene by converting from grams to moles. Total pressure is 0.989 plus 0.118, or the argon pressure and the benzene pressure in atmospheres, or 1.11 atmospheres. Finally, we're asked for mole fractions. So what is the mole fraction of each gas inside the flask? Divide partial pressure by the total pressure. Mole fraction of argon is 0.981. Mole fraction of C6H6, or benzene, is 0.106, which we find by taking the C6H6 pressure and dividing it by the total pressure. Or we could take 1 minus 0.981, well, that gives us 0.109. Either example would be acceptable for the mole fraction of C6H6. They are the same within the limits of precision of these numbers. This concludes the third lecture for Unit 9.